Hey, this is Eric Wasatonic, and today I'm going to use my high voltage differential probe to look at the difference in the applied tank circuit voltage depending on whether I have my double resonant solid state circuit or my rotary spark gap circuit hooked up to the primary tank circuit of my Tesla coil. And I got a very simple drawing block diagram right here. There you can see the rotary spark gap driver and the double resonant solid state driver. They are alternate. I can alternate between the two of them with my big old Frankenstein switch right here, and then I'll be measuring the voltage directly on the output of that switch. That's the input tank circuit voltage into the primary and the primary capacitor and the inductor, the primary coil. And this is what I'll be using to take those measurements. I got my digital scope here all set to go. Each probe is on a different channel here, and I'll just use the math function to take this to do channel 1 minus channel 2, or VA minus VB. And put on my headphones, turn on the spark gap motor. And there's a look at what I captured. You can see the yellow one is channel 1, the blue one is channel 2, and from here to here is 1/60th of a second, so I'm running on 120 breaks per second. And for each one of those breaks, you can see that the voltage going into the tank circuit, VA, is has a magnitude of about 10 kV. I'm running at 10 volts per division times 1,000 because of the voltage probe. So 10 kV, or let's say negative 10 kV minus a positive 10 kV gives me the math function down here, a negative 20 kV. So that's the wide view of it. Now if I zoom in, then we can actually see the 100 kilohertz oscillation of the primary tank circuit, and you can see how the voltage just goes down, or at least the magnitude goes down very rapidly to only a few kV per channel. And let's see the math. Let me put that on a better scale. There we go. See, the voltage drops from 20 to about 8, and then oscillates a little bit as it dies down to 0. Now I'm going to switch over to the solid state circuit. Got some switches to flip here. Turn on the function generator. Throw my Frankenstein switch. Time to collect some data. Now it's time to analyze the data. And again, this is the wide view. You can see I've got one pulse, or one turn on pulse for the solid state circuit every 1/120th of a second. And the first thing I notice is channel 2, during the off time, is pretty flat around 0 volts, but channel 1 goes up and down a little bit, plus minus 100 volts or so. I'm not sure why that is. Let me zoom in. on this one, and we can see the high frequency part of it. I guess I'll separate them. Well, first let me look at the phase. See, yeah, you can see at first channel 1 and channel 2 are 180 degrees out of phase, but as they move along they get to be almost in phase with each other. Just a few degrees offset. If I zoom in even further, we can see some spikiness going on here. Okay, I had to stop and think for a minute what was going on here. Each one of these little sudden changes in the voltage, that's when the IGBT H bridge is switching polarity, you know, as it switches with the current feedback from the primary circuit. That's when it switches polarity, and then it powers up the primary tank circuit and with the opposite polarity, and gets current going in the other direction. I was expecting each of these to be simply a square wave, or just 180 degree apart, and then the math function would simply be another square wave with twice the magnitude as each one of these. But that's clearly not the case. I think I may have, you can see there's kind of a square wave function to it. But anyway, as far as magnitudes are concerned, you can see channel 1 is, we're looking at 5, this translates to 500 volts per division, so we're looking at, looks like about 1,000 volts peak to peak, or just 500 volts peak. Channel 2 is about half that, and the math function, well, the difference between them, that's a little more than 1,000 volts peak to peak. Now I'm going to take a look at the other end of it, and so I had the function generator set for a 200 microsecond duty cycle, so we got the 100 kilohertz oscillation buildup, the buildup for 200 microseconds, and then right here in the middle is where it cuts off, and then the primary circuit is left to resonate on its own. And we got a lot of interesting stuff here. See, right about there is the cutoff, and then we just got some weirdness going on here. I don't know what these two, I don't know what these spikes are for. I think what's going on at this point is I've got some weird interaction of the top load discharge and the secondary current feeding back into the primary circuit and making all these weird voltage loops here. I'm going to run it at a lower power to see what we get. And here's what we got. This one looks much better. You can see it's the voltage starts to build up very slowly from here to here for 200 microseconds, at which point it just decays very gradually all by itself for a period of time. And I think that it just takes a longer time to decay because the secondary circuit is not, it's not discharging a lot of energy through the spark gap discharge, for the sparks coming out of the top load. I'm going to take one last measurement here. I'm going to look at the current, the primary current going through my Pearson current monitor, the big green donut there, on channel 1, and channel 2 is going to be hooked up to the single output of the Tektronix P5200 high voltage differential probe, which I can look at. I can actually use that on the solid state side of the Tesla coil, but certainly not on the rotary spark gap side because the voltages are just much too high on the spark gap side. So I'm gonna see what I get on the scope. look at that. Now this is much better. Here you can see this is the primary current at 50 amps per division, starts at 0 to 200 microseconds, builds up, and then a die down as the switching turns off right here, and you can see it's much closer to a square wave than with the previous high voltage probe setup. Look at that. That's what I want to see. Just a single clean square wave. We're looking at 250 volt per division. Yeah, we're looking at from 0 to 250 volts on each output terminal of the H-bridge assembly. And you can see right here at this point, that's where it switches off, and then the primary circuit is left to fend for itself as it dies down for a few more cycles of the 100 kilohertz wave. You can see that the peak value of the output here is from 0 to only about 120 volts, plus minus 120 volts square wave. That's really, really nice. That's what I was looking for. Well, there you go. We got a lot of data today, but unfortunately most of it is going to have to go in the trash because of these things right here. These are Tektronix P6015 1000 time high voltage probe. Let's see, 20 kV maximum DC continuous, and they say above 100 kilohertz see derating curves. So that essentially means that this has a 100 kilohertz bandwidth, and since I'm operating at 100 kilohertz with my Tesla coil, these are unfortunately not going to work. So this thing with a 25 megahertz bandwidth gives much better response. The only problem is I can only use it on the solid state circuit directly. If I want to use it on this thing right here on my rotary spark gap, I'm going to have some kind of a voltage division thing going on to lower the voltage. I really don't know what I'm going to do there, but I can figure something out. So thanks for watching. See you next time.